Hello, everyone. We will start our session now. Thank you all for joining us in our fourth session of the series of Embracing AI in the Geospatial field. We are glad to have Dr. Ghandour as our speaker today. He will present about how segment anything would revolutionize Geospatial application. Sorry. So Noha, next slide, please. Our moderators today will be Dr. Noha, she is Events and Training Coordinator. Juliet, she is the Western African Zonal Coordinator, and Safinaz Mubarak, me, Northern African Zonal Coordinator. Next one. Dr. Noha, she will tell us a short brief about our community in 5 minutes, and we will start with Dr. Ali after this. Dr. Noha.
Okay. Hello, everyone. Thank you for your attendance today in this session of our series, Embracing AI in the Geospatial field. This session and this series is organized by African women in GIS community. Thank you, Dr. Ali, for your accepting our invitation. We are honored to have you today. I will start with a brief about our community. Okay. We are a community made up of African women around the world who work, study, or are enthusiastic about the geospatial industry and its related fields. Our community, throughout our activities, aims to allow its members to be themselves, create networks, gain mentors, get career advice, partake in geo projects to improve their portfolios, access job opportunities, as well as geo course information, and showcase their work to the world. So for further information about the community, please stay to the end of the session. Juliet will present an introduction about the community, about our vision and activities by the end of the session. So now back to Safinaz to start our session.
Okay, thanks, Dr. Noha. Please, next slide. Now, let's move to have a brief about our speaker, Dr. Ali Ghandour. We are glad and thankful for him to accepting our invitation to present this session. Dr. Ali, he is associate researcher at the Lebanese National Center for Remote Sensing, National Council for Scientific Research. Dr. Ali had his PhD in computer communication in 2013. He was the Toyota Infotech Labs at Mountain View, USA before joining CNRS in 2015. He is the founder of the Geospatial Artificial Intelligence GeoAI Group. GeoAI Group ranked 4th in the NASA Harvest Fault Boundary Detection Challenge. He is also the coordinator of the Lebanese National Technology Transfer Network between 2015 and 2017. He has more than 40 publications with special research focused on geospatial urban sensing, transportation, water bodies, monitoring, and crop yields estimation. He made research contributions to vehicular cognitive networks and IEEE 16909 Standard Working Group. You can follow Dr. Ali on social media. We'll send his social media links on our chat box. And also you can ask your question and send it to our chat box in Arabic or in English. You are free to do in which language, in English or Arabic. Dr. Ali? floor is yours. You can unmute yourself and start.
Hello.
Hi, Dr. Ali. I'm
Thank
really
you,
glad you are welcome. It's our pleasure to have you today, and hope it's not the last one, last time to have you. We hope to see you in the next sessions.
Thank you, Safinaz, for your nice introduction. I'd like to start by welcoming everyone who joined us this afternoon. It's a Friday afternoon, so I'm really glad that we're having this talk. I'd like to apologize for my voice. So, like Safinaz, I got the flu, so I'm having issues with my voice.
Oh, it's okay.
Okay, so let me share my slides.
Okay, go ahead, please.
Okay.
Maybe you need to stop. Yeah, maybe.
Okay.
Thank you, Dr. Noha. Okay. So the structure of my talk would be as follows. I'll start by a general introduction about remote sensing, AI in general, then talk about deep learning models. When I have all this context there, I will move towards SAM. Then after presenting SAM, Ali and Hassan, two graduate students and a research engineer from the GeoAI group, will present a live demo about how we are using SAM as part of our research. So okay. A brief introduction about CNRS. CNRS is the National Council for Scientific Research in Lebanon. It was established in 1962. So last year we celebrate our 16th anniversary. At CNRS, we have 4 centers. Center for Geophysical Research, which is related to earthquake and any geophysical movement. We have a center related to marine science. We have a 3rd center related to atomic energy. And the 4th center, which I'm affiliated with, is the National Center for Remote Sensing. So I'm an associate researcher at the National Center for Remote Sensing. And at this center, I've established, as Safinaz mentioned, I've established the GeoAI group. So what we're doing at the GeoAI group, we're at the intersection of geospatial studies using AI technology. We've been involved in several projects. I'm sharing on this slides a few of them. So we worked on a project related to urban AI mapping. So we used deep learning techniques to autonomously detect buildings. And we used that to generate the first comprehensive national-wide building in Lebanon. So now we provide an online layer which has around 800,000 buildings in Lebanon. And we're continuously working to update this map. And a lot of application has been built on top of that map. So to name a few of them, for instance, the solar rooftop potential map. So using those footprints, we can generate an estimate of how much solar rooftop we can harvest in each building in Lebanon. Another project we're involved in at the GeoAI group is related to crop monitoring. So we map on an annual basis the 2 major cash crops in Lebanon, which are wheat and potato. Another project is related to water body monitoring. So we use satellite images to monitor water body in Lebanon, which is the Araon water body. On a weekly basis, we fetch new Landsat or Sentinel-2 images. We estimate water volume. We generate a couple of indices related to water quality on the lake. And I'd like to mention a last project related to road crashes observatory. So since 2015, on a regular basis, we are monitoring road crashes in Lebanon and reporting an observatory which has data and features related to road crashes, which can be used by researchers to build on top of them. So that was kind of a quick interview about the GeoAI, but let's move to today's topic. So today I'm gonna talk about some, but before going there, I'll start by talking about remote sensing in general. So remote sensing has started, the concept has started in the 19th century, in 1840s, so in the mid of the 19th century. Back then, we didn't have satellite, we didn't have airplanes, we didn't have drones. So back then, so the first instrument used was balloons. So balloons were used to take imagery from above, so observing Earth from above. Then there were a trend which has been widely used in Europe to use a pigeon equipped with camera. So this might look naive nowadays, but back then this was the latest technology. So they used to have pigeons equipped with camera, and they used them to capture aerial images. And then airplanes were first used by military to take images, and also it started to take manual images, and then automation was introduced. So this is a bit of history about remote sensing. Let me talk about the different platform. I'm not sure if the resolution of the slide is good enough and that you're able to see the different platforms. So the platforms can vary from satellites, which are at the orbital height, to balloons, to aerial images that can be captured either by airplanes or by drones. Now UAVs is taking a huge momentum, all the way towards CCTV cameras, which are at the road level. Okay, so a bit of background about DIP, which stands for Digital Image Processing. In DIP, we have three basic problems. The first one is classification. So I'd like to know the object that is available in a specific image. So in this case, the first image was passed. Okay, so this image was passed to a classifier, and the classifier, with a confidence of 97%, mentioned that this image has a dog, and with a confidence of 3%, that it has a cat. So this is a basic classification problem. The second category of problems, we call it object detection. So given a certain image, we are asking the model to identify, to put a bounding box about the various objects available on this image. So in this case, we can see that in this image, we have cat, which are labeled in the red bounding box. We have a dog, which is labeled in the blue bounding box, and we have a duck. We have duck, which is labeled in green. Yeah. Okay. So here I reach the third basic category in digital image processing, which is segmentation. So classification and object detection are not the focus of today's talk. Rather, our focus is on segmentation. Segmentation itself is composed of two approaches. Now, some researchers talk about a third one, but let's focus on the basic one on semantic segmentation and instance segmentation. So here in this example, you can see an input, a satellite image, which was passed to a semantic segmentation model, and the output is depicted on the right. So the figure on the right is showing the mask which was fetched by using semantic segmentation from this image. So buildings, for instance, were colored in dark blue, roads were colored in cyan, and water was colored in yellow. So there are different objects, but we have the same color for each object, for each class of objects. So all buildings are labeled with the same color, which means that all buildings are grouped as a single mask, as a single layer. In semantic segmentation, we are not able to differentiate between objects that belong to the same class. So here, the buildings are all grouped in a single mask. If we want to fetch individual buildings and give them an ID for each building, this needs a post-processing step. So for instance, we use watershed as a post-processing step to extract single buildings. So this is semantic segmentation. I hope you're already familiar with it. Instance segmentation. In instance segmentation, each object of the same class has its own ID. So if this is from a very famous instance segmentation data set, it's called ISED. It used to be one of the largest data set, but the technology is varying rapidly. So in ISED, as you can see, in the second row, for B is semantic segmentation. For a semantic segmentation, all airplanes, for instance, or in the first row, all ships, all yachts, have the same color because they belong to the same class. And as I just mentioned, in semantic segmentation, all objects that belong to the same class are grouped together in a single mask. Whereas in the last column, in column number C, which is the instance segmentation mask, you can see that each airplane has its own color and each yacht has its own color. This is to reflect that each one of them has its own ID. And then we can easily transform it to a shapefile, and each one of those objects will be an independent polygon and has its own polygon ID. So this is the basic difference between semantic segmentation and instance segmentation. Again, our focus for today's talk is about instance segmentation. Okay, so I've introduced remote sensing. I've talked about the main DIP techniques, which are classification, object detection, and segmentation. In segmentation, I've mentioned two classes, two subclasses, which are semantic and instance. There is a third one, which is called panoptic, but we'll not talk about it today. So to be able to autonomously generate those masks, so those masks here in this image were manually labeled. And manually labeling, which we call annotation, manual annotation, is very expensive. It's time expensive, and of course it costs a lot. So we'd like to use our algorithms to be able to generate those masks. Okay, I'm sure most of you have already seen this figure a couple of times. So we have a general domain which calls artificial intelligence, AI, which is nowadays a buzzword. So a lot of products now in the market or in the internet claim to be using AI, even if they're not using AI. So AI, we're trying to make our machines, our computers, behave like a human, or even not a human, even other living in the earth have a lot of intelligence in them, living beings. So this is AI. A subset of AI is called machine learning. So in machine learning, we try to use data input, and those data we try to provide some manual features and let the model learn those features. Machine learning famous examples are support vector machine, random forest, and a lot of our today's problems can be solved using machine learning. So we don't have always to refer to deep learning for any and every single problem. So that's why we need always to understand our problem and formulate our problem well to be able to know what is the technology to be used to solve it. A subset of machine learning is deep learning. Well, in deep learning, we're trying to mimic our brain. The way our brain is working, the neurons connection in our brain, we're trying to mimic it in deep learning. So in deep learning, in machine learning, usually we pass the features ourselves to the model. In deep learning, the model extracts the feature itself. So we're not passing the feature ourselves to the model. This is why there is a huge research field nowadays, and we are doing a lot of research at the GOI group in what we call XAI, explainable artificial intelligence. Nowadays, using deep learning, the model will extract the feature itself, and we interact with the deep learning models as black boxes. So we don't know what are the features extracted by those models. They are fast, they are very accurate, but we'd like to know what are the features that the model extracted. This is why there is an emergent field called XAI, which is of course beyond the scope of today's talk, but I wanted to just have a pointer about it here. So in deep learning, we go through the classical approach. We have a training set, a validation set, and a test set. And we need to always make sure that there is no leaking between those three sets. So there is no data that is available in the test set and in the training set, because this would hinder the performance of our model. So what we do in deep learning is we go through iterations. Those iterations, we call them epochs. In those epochs, we pass our training set and our validation set to the model, and then we use the validation set to fine-tune the hyperparameters of the model. Each full iteration where the model has seen the whole training and validation set, we call it one epoch. So we go through several epochs until we believe the model is performing well and is no more learning. So there is no need for additional epochs. Hopefully, we reach an optimal model, although here optimality is not the question. We're not looking for optimal model, we're looking for a good enough model. So if we reach a good enough model, then we test this model on a test set which the model has never seen before, and we use it as a reference, as a benchmark to evaluate our model. In deep learning, the classical approach, which has been there for years, is CNN, convolution neural network. But also, there is a trend now which is using transformers. So again, in deep learning, let's think about it as two subcategories. One of them is to use convolution neural network. This is a technology, and another technology which gonna use transformers. Each one of them has its pros and cons, but for large data sets, SAM is an example of those large data sets, transformers are performing better than CNNs. Okay, so if we train a certain model, a model for crop detection, for water detection, for building detection, for solar panel detection, any kind of model, if we design a certain model using a training set, a validation set, and a test set, this model, if we train it in a good way, would provide guarantees on those sets, on those scenes that the model has already seen and is familiar with them. But what happened, what if we need to train our model on a new data that is different from what the model have seen? Not to train, sorry, what if we need to infer our model, to use it, to apply it on data that the model has never seen before? So as you can see on this slides, so aerial images have a lot of temporal changes. So the same scene will look different in various seasons across months. Also, the same objects, so a farmland in California will look totally different from a farmland in China. So those changes, this is what we refer to as out of distribution generalization. So the model provides guarantees on data that the model has already seen, has been already trained on. But what about data that the model has never seen? Okay, we're getting some question for the audience. Let's answer those at the end. Maybe it would be better. Okay, so since we're trying nowadays to use those deep learning model in practical scenarios, so we're not using them in the lab anymore. Those deep learning models are being implemented in market, and they are being used in various scenarios, and we need to guarantee that those models would be able to generalize out of distribution. So let me give a last example to illustrate this idea. Let's assume I'm riding an autonomous vehicle. So I'm riding an autonomous vehicle and it's taking me towards work. And the computer vision system of this autonomous vehicle is taking charge of the navigation. And then the computer vision system of this autonomous vehicle noticed a scene that has never been trained on. So let's say the model is trained to detect the red and orange and the green of traffic lights, but some emergency happened and there is a police that is on road and he's taking charge instead of those traffic lights. So he's overriding those traffic lights. The autonomous vehicle need to be able to generalize, and any deep learning model that we are deploying to the market need to be able to generalize out of distribution. So this out of distribution issue is has gained a lot of attention in the past few years, and there's a lot of research related to out of distribution generalization. And one of the concept that was coined back in July 2022, so this is less than a year ago by researchers at Stanford, is foundation models. So they suggested that we stop training small models for small tasks and rather rely on large foundation models. So those foundation models are large deep neural network model. They are trained on a huge data. They have billions and trillions of parameters. Usually they are multimodal. What we mean by multimodal, so they don't take only one single type of input. So let's say they are trained using images, or they are trained using text. So those foundation models are usually multimodal. So they are trained using images, text, videos, sounds. So they can process several types of images, of inputs. And those models, they can be adapted to various downstream tasks. So they can be fine-tuned to achieve a lot of downstream applications. A very famous example of foundation model is now we call them LLMs. Not all LLMs are foundation models, but some LLMs are part of are considered as foundation models. So I'm sure you've all heard and are being using now, and you're using now ChatGPT. So ChatGPT 3, for instance, it had 175 billion parameter. So those are, when we talk about foundation model and LLMs, large language models, so those are usually transformers based. So ChatGPT 3, as I mentioned, was made of 175 billion parameter. ChatGPT 4, they didn't release how many parameters they use. There are several speculations, but we're talking in the order of trillions of parameters. So if we need to make some sort of analogy between those foundation models and our human brain, so a researcher, they estimate that our human brain is made of approximately 86 billion neurons and 100 trillion synapses, but those are used for a lot of functionalities. So not all of them are used for text recognition and image recognition. So here, so I made this analogy to show you that we are talking about extremely large models that need a lot of machines to be used, that need huge computation power. So there is some article I shared recently about the amount of water needed to train those models. So there is a huge amount of water needed to cool the server rooms used to train those models. We are talking about a huge budget in the order of hundreds of thousands of dollars to train a single foundation model. Okay, so in the past maybe 20 minutes or 25 minutes, I didn't even talk about SAM. So I was laying the foundation of remote sensing, the IP, deep learning, CNN versus transformers. And then I talked about out of distribution, generalization, and why we need foundation model. SAM is a recent example of foundation model, which is the first foundation model in the segmentation domain. So it was proposed by Meta, used to be known as Facebook AI. It used to be known as FAIR, Facebook AI Researchers, now known as Meta AI, in April 6, 2023. So this was coined very recently, like a month and a half ago. So the objective of SAM stands for Segment Anything Model. The objective of SAM is to be able to do segmentation without the need of any additional training. So as I mentioned in the past, for every specific task, we used to collect data sets and do training, and then apply our model for this specific task. SAM is suggesting now, this is why it's a revolution in the segmentation domain, is suggesting a tool which can be used to do semantic instance segmentation without training. Okay, a few details about SAM. So SAM take various input prompts. So we can pass a point to SAM, we can pass a bounding box, or we can pass a mask. And it was designed to be ambiguity aware. So what do I mean by ambiguity aware? I'm not sure if there is a pointer here. Okay. Let me use the annotation. So here, let's say, in the example here, in the second column, so we passed this single point to SAM. So SAM has three scenarios here. We might need to simply segment this portion of the bag. So this is called in SAM terminology a sub-part object. Or we might be interested in segmenting the whole bag. This is a subpart. Or maybe we wanted SAM to segment the person who's having the bag. This is the whole. So since with a point input for SAM, there is some of ambiguity. SAM would not be able to know what exactly we wanted to segment. So this is why it's gonna generate for each input point prompt 3 masks. A mask called whole, a mask called part, and a mask called subpart. So again, we see here for the Zurich, so we have a point on the Z. So we might need SAM to segment the letter Z, or maybe we wanted SAM to segment the whole Zurich word, or maybe we wanted SAM to segment the whole plane. So to be able to provide different choices for the user, SAM will return 3 different masks. those we see them in a few minutes in the live demo that Hassan and Ali will share. Okay, so how was SAM trained? So to train SAM, researchers at Meta AI, they have prepared a huge data set called SA1B. It has 11 million diverse objects. It has 11 million diverse images, sorry, and those are high resolution images. And also it has 1.1 billion masks. Most of those masks were auto-generated. We will not talk about how they were auto-generated, but rest assured that they were generated with a high quality. So those masks are guaranteed to have very high quality, and lot of expert assessment was made to make sure that those masks have high quality. So this is significantly larger than any existing instance segmentation data set in the literature. This is a quick overview of the data set. Okay. My last couple of slides before moving to the live demo. So Zeroshot, maybe I had to add this slide about Zeroshot. So Zeroshot is a concept used in deep learning where when we try a model on a data set that the model has never seen. And thus, if the model performs well in a Zeroshot experiment, then it's able to generalize out of distribution. So here, researchers at Meta AI, they have tested SAM on a data set called BSD 500 for edge detection. As you can see, SAM was able to perform better than the ground truth data, which is really insane. So as you can see here, in the ground truth data, those edges were not labeled. But SAM was able to reveal them. Also, here for the vegetation example, SAM was able to detect edges that were never labeled in the ground truth data. Again, another example for Zeroshot testing of SAM, which is on instance segmentation. So here again, I'd like to emphasize that those data sets were not seen by SAM during training. So in this data set, SAM was able to perform again extremely well, and it was able to detect a lot of details that are not available in the ground truth data. So a last experiment provided by a researcher at Meta AI, they use SAM with a text prompt. And Hassan is gonna show us a real demo about this. So here, they passed the text prompt a wheel. This text prompt was passed to SAM, and SAM was able to segment the wheel. This is very important because here we'll be able to ground, we call it visually grounding. We're able to visually ground object using text. So the user will input the text, and based on his text, he'll be able to get the related objects in the image. In terms of adaptation, SAM is already available as part of the deep learning models provided by Esri. So Esri, as part of their toolboxes, so they provide around 60 or 61 deep learning models. SAM is one of them. Also, it was ported to QGIS. In terms of annotation business, so part of the disruption that SAM is making to the geospatial value chain. So annotation and labeling was a large business, and a lot of companies like RoboFlow and Pictera and Descartes Labs were offering labeling solutions. So those labeling solutions, now those companies are relying on SAM in their back end, which is really meaning that those businesses will struggle to survive in the SAM era. So those are few video examples from RoboFlow and from Pictera, where all those annotation tools has already embedded SAM as part of their pipeline. Let me skip those for time constraint. This is Descartes. This is even related, so there is an extension for SAM for tracking tasks. Okay, so my last slides. So at the GeoAI group, we are using SAM to enhance our GeoAI Urban AI tool. So I'm not sure if you already have a look to this tool. This is a tool where we provide the user open access where you can upload your own images and get the segmentation mask for buildings out of them. And also we have a different vertical of research where we're using SAM and additional text prompt to search inside satellite images. So a sample text prompt would be, show me wheat fields, highlight clean water bodies, show me buildings with solar rooftop panels. Those are examples of prompts we're working on. So I'm gonna move now to the live demo. Ali, a graduate student at GeoAI Group, and Hassan, a research engineer at GeoAI Group. I'm not sure, Safinaz, how much time we still have for the live demo.
We have more time for your students.
Okay.
They can take much time as they want.
Thank you.
We don't have limited time.
Okay. I will share, so maybe it would be nice for the audience. I will share the link of the notebook that Ali and Hassan gonna use. So I'll share it in the chat. So it's already there. Yeah, it's already there. So I guess those who are interested to follow up the demo with Ali and Hassan can be simply open this notebook.
Okay, can Ali and Hassan raise their hand that you can make him co-host and they can share their screens? Okay, Dr. Noha, please.
Okay, hello everyone.
Okay, thank you for your support. Okay, the floor is yours, Ali and Hassan. You can start.
Can you see the screen?
Yes, it's clear.
So I'm going to show you a live demo of SAM using the meta demo release. So here I uploaded an image from Google containing several candies. You have the option of choosing from a gallery meta release containing some images from the dataset. So here we have different types of prompts, everything which segments everything in the image. So let's try this first. So if we can see now. So as we can see that every candy is segmented with a different color. And also we have the option of cutting out all objects. So if we press here, we can see that, just a moment. We can see that we can save objects as a single image. Yani saving images, saving objects in images like here, save images. So now let's inspect the bounding box as input prompt. So if I want to segment this candy, so I just draw a bounding box around it, as shown here. Let's try another example. So if I want this candy, so that's it. So also we have the option of cutting out object. This cuts out this specific object. And now we will go through the single point as input prompt. So we can hover or click on the object. So just like here. Or we just can click here. So here, as Dr. Ali said before about ambiguous prompts, so as a user, maybe I didn't want to point, I want to segment the whole candy, not only the star. So here we have the option of multi-mask. So if I press it, we can see that we get 3 masks, the whole, the part, and the subpart. The whole contains the whole candy with its wrapper, the tail, and the head. The part contains the body or the actual candy. And the third contains only the star that I pointed out. Also, we have the option of cutting out objects. Unfortunately, inserting multiple points won't give a good result. Just like here. As we can see, it segmented an object that I didn't point out. So we need to use this feature, the remove area. So if I press it and put a point here, this point is called like a background point. So here we had these 2 objects segmented. So now my colleague Ali will show you a live implementation of SAM on a remote sensing data.
Okay, hello all. Thank you, Dr. Ali, for presentation. And now I will show the live demo of that Dr. Ali provided the link with. Okay, if you are using this demo now, you can before you can start, but make sure to change the runtime to GPU in order to run the code. You can also run all the cells after each others by run all. First, we are going to download the samples data that needed for this demo, and then we are going to install the dependencies of SAM, and then importing the necessary libraries for this demo. Okay, here we are going to load the model, that is the weight file of the model that is provided by SAM. And first, in the first experiment, we are the first purpose. The first experiment, the purpose is to extract a mask of building in an image. So using a single point prompt, as Dr. Ali discussed before, first we customize the code for single point. in order to take each building, then we concatenate all masks together in order to get a mask tile which contain all building masks. As we can see here, the first mask, here we are making multi-mask output, which is recommended for single points. As we can see here, the mask of each building, the mask one, which represents the sub mask, and here is the sub. Okay, and here is the whole mask. And we are talking about each building mask. The results are always better in the results are always better in the second and the third mask, better than the first one. So as we can see here, and each score is viewed here. And mask one score is 0.4. The score is the IOU. Okay, the third mask is with highest score. Okay, the second is experiment. We are going to show we are going to take a batch of boxes to prompt some about the building's mask. Here we are not using a single point. We are using a batch of boxes. Yani each building is prompted as a box. As we can see here, the prompt, which is a box, and here is the output mask of the building. Okay, here you can see the results that are saved in this file, which is scored. You can see all the score results, which is the average score for each building, which is 0.9. Okay. Now Hassan will continue the Langsum demo.
Okay, so hello again. I'm going to show you now the Langsum, which is SAM using textual prompts. So here, as Dr. Ali said before, Meta released or mentioned in their paper about SAM with textual prompts, but they didn't release the code yet. So many developers and researchers started to work on combining or using textual prompts for SAM. So here is a model called Lang Segment Anything or Langsum that combines two models, a grounding dyno and a segment anything model. Grounding dyno is known to be an object detection model. So this model works as follows. First, the image and the text prompt, which also called a query, are inserted to the model, the grounding dyno, I mean. Then the grounding dyno returns text embeddings and bounding boxes of the objects we need to segment, according to the text, of course. And finally, it filters them according to certain thresholds, as we can see here. We go down. The code that I skipped are loading the model. So as we can see here, there is a box threshold and a text threshold. So I want to note here that the optimal threshold can vary depending on the quality and the nature of the images, as well as the specificity of your textual prompts. So you need, these thresholds are tunable, so you need to change them to get your best results. And now I will run this code on an image or a tile from a WHU test dataset, and having a house as a textual prompt. Hopefully it will take less than a minute. So I'm running it now. Sorry for keeping you waiting يعني بس.
This is our last demo, right, Hassan?
Yes.
Okay, so in this demo, Hassan is inputting a text. Which specific text do you use?
House as an input text here.
Okay.
So as we can see here, the results finally came. So here we have the original image, and here we have the images with the masks or the predicted masks. So as we can see that approximately all houses are segmented well. And here we have an accuracy score of 0.83. I would like to try more samples, but maybe it would take more time. So I will try one more.
Yeah, I guess the audience has now access to the collab and those sample images. So maybe you can test them on the background, Hassan, while we open the floor for question and feedback and discussion with the audience. Dr. Noha, Mrs. Safinaz, the floor is yours.
Okay, we can now take the questions. Dr. Ali, we have some questions. You can answer it.
So we have questions.
Yeah.
Where exactly?
In the chat box. I will send them.
Okay. So yeah. So
okay, I can say them.
Yeah. Please go ahead.
Okay.
Yeah.
First question, you said for big data to transfer better that AI technique. Is this also for special data and raster data?
Yeah, it does. Yeah, it does generalize for different kind of data.
Okay. What does the score of the mask represent?
So it's IOU. It's
Yeah.
intersection of a union.
Yeah. Oh, yeah. Okay. And the result will be a shapefile or not?
Okay, this is a good question. Since it's instant segmentation, so we can simply add a couple of lines. So if the audience is interested, maybe we Ali and Hassan can update the code after the webinar. We can add a couple of lines, so one or two lines. So now I guess Ali, the data is being stored as a Panda data frame. So we can, so we can simply export those GeoPandas to a shapefile. Yeah, so this would be doable in a couple of lines of code.
Okay, that's great. So your student Ali and Hassan can edit the code and reshare it with us.
Sure.
Yeah, because especially I will use it.
Yeah. So maybe I didn't mention this. I should have mentioned this 1 hour ago. So at the GeoAI group, all the team, including myself, are either computer engineers or computer scientists. So this is why we are building we've been building for the past 8 years our toolbox written in Python and in PyTorch. So we are not using off-the-shelf solutions such as Esri, ArcGIS, or ERDAS, or Envy, or QGIS, or Incognito. So we're not relying on those tools, but we are building our library ourselves in Python. And for deep learning, we're using on top of Python a library called PyTorch.
Yeah, that's great. Okay, we have another question. In this example, for house, the accuracy is around 0.8. So this for number of house that detected, or the shape of the house.
Okay, so Hassan can answer better how he measured accuracy, but I guess accuracy was measured on a per building basis. So for each building, we are comparing some predictions versus the ground truth on a per building basis. Hassan, can you elaborate on this one, please?
Yes, this results show the number of houses, not the shape of the house. But maybe you detected that they're changing in colors. So if I share again the screen, just a minute. Here you have a dim blue or dark blue, and here you have a light blue. But this is because when displaying the results, we are placing the mask on top of the houses. So as you can see here, we have the house as dark. So placing blue above dark color increases its brightness. So that's, I think that's what he meant.
So maybe the question was by Anas. Maybe Anas can elaborate a little bit more on his question.
Okay, Anas, you can raise your hand and we will unmute you. So you can clarify your question.
Hi, first of all, thanks for everyone for this presentation, and you have a nice tools. And it's just if I need to mention this, as you said, it's existing for some software like Esri, Envy, and other software for remote sensing, but it's something to build these tools and you can modify it and update it. So thanks for everyone. My question about the accuracy, I mean this number of accuracy, it's related to how number of houses he detected in the image. So this, like for example, we have 1,000 and he detected like 900, something like that. So the accuracy for this, or the accuracy related to the shape, how is accurate to drawing the shape for the housing. And
oh, okay. Yeah, I got it, Anas. So actually, thank you for your question. Actually, it's both of them. So if there is a building that the model has missed, then this will lower the accuracy, the reported accuracy. And if there is a building that was not detected in a very complete way, so part of it was detected, this would also reduce the accuracy. So to have a 100% accuracy, we need to be able to detect all those buildings in the same shape that they exist in the ground truth data.
Okay, I think he gets the answer. Okay, Hassan, did you finish? Okay, I think you're not.
Yes, thank you.
Okay. We have another question from Stella. Can you raise your hand? We will unmute you.
Hi, can you hear me?
Yes, yes, we
Okay,
can.
thanks to the presenters for such an insight on the SAM model. I've seen that a lot of examples in using this model usually leverages high resolution inputs. And I'm wondering if you have any experiences in using this model for, say, moderate resolution satellite imagery, like that from Sentinel-2 or Landsat.
So thank you, Stella. This is a very nice question, actually. We didn't experiment with SAM on Landsat imagery, so I don't have an answer for a 30-meter resolution imageries. But we had a couple of experiments for Sentinel-2 data, and its results are pretty well.
All right, that's good to know. Thank you.
Sure.
Okay, we have another question. Are you try the model on slum area? If yes, what about the accuracy?
Yeah, so this is a very practical question from Hamad. I appreciate it. So we had an experiment last week with Maps Geo. I'm not sure if Mr. Mu'tasim is among the audience today. So we had an experiment for our models on a slum area where they did the manual annotation, and we were surprised that the model results were really accurate. So the results on slum area were pretty well. They had very good accuracy. And this enables such models to be used in practical scenarios for building segmentations, building rooftop segmentation.
A question from Dr. Haifa. If you apply SAM on crop monitoring, can I separate each type as clean or invested as example?
Okay, so I guess Dr. Haifa is asking if SAM can differentiate different types of crops.
Yeah, crops, yeah.
Yeah, so in our research, we didn't use SAM yet for this task because for this task, to be able to detect a crop phenology, as you know, we need a time series of data of usually multispectral data. So we didn't experiment with SAM, so we're using different other transformer models for this task. But I guess it would be a nice experiment to extend SAM to accept a time series as input and to test if it's able to do crop type detection.
Okay, thanks, Dr. Ali. Dear audience, if you have any question, please send it to our chat. And if you want to talk, please raise your hand. I think we don't have any questions. Can you use SAM to get airplane as shapefile?
Sure, definitely. Yes, so if we have an aerial or a satellite image, and we can use it, use SAM to segment those images, those airplanes, and export them as a shapefile. Sure.
Okay. Can you please show us again how to use or run the tools? I think if you don't have time, maybe we
Yeah.
will. Okay. Okay. Go
Yeah,
ahead.
I guess there is no time to do it again now, the demo,
Yeah.
but
Yeah.
we've already shared the link on the chat, and this is a collab link. So simply you can hit run, and the cells will be executed one after another.
Also, we will upload the recording video on our YouTube channel once we finish it, and we will share it with the presentation with the certificate link. I think Dr. Noha sent a form. You can fill it, and we will receive the video link and certificate of participation. Okay, Stella, Dr. Noha, can you unmute her? I think she has a question.
Hi, I have just this one last question about pre-trained models. So usually these models are trained on very huge amount of data sets, but I'm wondering the mystery behind and why it really works when you pick up this model that was trained on an entirely different domain and adapted to like a new set of tasks, but somehow it does work. So what is the reason why this is the case?
So as I mentioned on the slides, the key idea behind Zeroshot, or what we call out of distribution generalization, is to design models that are able to have good performance, models that performed well on test set that are totally different from the training set. So let's assume this as an axiom. Let's say this is an axiom that those foundation models, because they have been trained in a way which we call a zero-shot approach. So those models are able to generalize well to scenarios that they haven't seen before. The theory behind this would be very technical to discuss now.
Okay. I mean, in case you have some resources that digs a bit deeper into the reasons, I'll be glad to have them. Thanks.
Yeah, sure. So I can share several resources about this concept right away on the chat.
Okay.
Okay, thanks all. Last reminder, if you have any question, please send it, or you can raise your hand. Okay, if not, I will thank Dr. Ali and his team, Hassan and Ali. We are really grateful for this wonderful presentation. I really enjoyed it. Especially, I I wanted to know how to run this model to use in my master degree. I'm really thank you, Dr. Ali. Now we will move to Juliet.
Okay, thank you, Dr.
Thank
Ali.
you.
And your team. Your presentation is informative, and we hope you get well soon, inshallah. Thanks, Ali and Hassan, for the demo.
You are welcome. Thank you.
Thank you.
Thank you for
Juliet
listening.
Juliet will start now to present about the community. Juliet, are you here?
Hello, yeah, I'm here.
Okay, I can share the screen from.
Can you hear me?
Okay.
Your voice is clear, Juliet. You can start.
Okay.
Okay, you can start now.
Okay. Good afternoon, everybody. Thank you, Dr. Ali, for this wonderful presentation, and to everybody that joined, thank you. So I'm going to give a brief history about African women in GIS, our story, our mission, and our goal. So, Dr. Noha, you can scroll down. So we are a community made up of African women across the world who study and enthusiastic about the geospatial industry and its related field. This community is aimed to allow its members to be themselves, create network, gain mentors, get career advice, taking projects and improve their portfolio, access job opportunities, as well as job cost information, and showcase their work to the world. So these are our members on the side. So our mission and our vision. Our mission is simple: to create a safe space for African women in. Oh, can you hear me now?
Yes,
Our
yes,
mission.
Juliet.
Okay, thank you. Our mission is to create a safe space for African women in the geospatial industry, irrespective of their career level. Then our vision is we aim to bridge the gender gap in the African geospatial industry. So what do we stand for? These are our colors. The leafy green is our love for nature and geo. Then pitch black is unity and support among members. Then light gray, gender equality. Then pure white, safety and safe space. Then who are we? Our history. This community was first started as two separate country groups. Chidinma started for women in GIS Nigeria around June 2017. Then Sienna started Women in GIS in Ghana, April 2019. In June 2019, Chidinma reached out to Sienna. They met on LinkedIn. They discussed their reasons for creating these respective platforms for women in their community. After that, the genesis of African women in GIS community happened in 2019. Then we had Nigeria, we had 41 members. Ghanaian members, we had 1. 11. Burkina Faso member, we just had 1. Then our growing community. So our community is growing with about 500 plus members residing in 30 plus countries. As of May 2022, we had most of our members residing in Nigeria, Kenya, Ghana, Egypt, and South Africa. So due to our growth, we are currently having 28 volunteers who help us run these organizations. So this is our growth. So we have 500 plus members, 30 plus communities. We have 9,000 social media followers across LinkedIn. So these are locations of all our members. You can see that. Then the problems that influence our existence. We have the male-dominated geo industry, lack of female role models and career guidance, inaccessible GIS jobs, and inaccessible and affordable GIS events and location and courses, then lack of GIS potential awareness, then lack of grassroots awareness. Then fundamental problems we have African GIS industry and other STEM fields are dominated by men. We all know that. Then lack of proper career guidance, then inadequate school curriculum, then lack of exposure to the African female GIS role model. Then we have lack of grassroots GIS benefits and applications, awareness among students as well as the public. We have the gender career tendency of, African parents. It's something we all know about. And we have career paths and problems. We have limited number of GIS related jobs in African countries, inaccessible GIS job information, and lack of female mentors for career guidance. We have inaccessible or unaffordable GIS event and skill upgrade courses, then no knowledge of the community membership. So how are we contributing to solving this? How are we contributing to solving this problem? Dr. Noha, you can scroll down. Solving these challenges. So our contributions include networking, learning, and mentorship, awareness. I'm sorry, can you keep scrolling down? Thank you. Then our membership is restricted to only women. Our webinars, events, and most of our activities are made public. It's free for everybody. So that is that for now. And Dr. Noha dropped the registration link for those who attended and who are not members. So these are our events. So this is it.
This is some of our activities, like internal events or member speaker panel events. Also, we have some active collaborations with other organizations and other communities related to geospatial field. We have in our this section in our website about our members. It's a public member section. Allow members to be conducted for speaking, consulting, jobs, and any other geo-related opportunities. Also, in our blog, in our website, we can find articles written by our members are published here for exposure. This articles are related to geospatial field and other fields. And our YouTube channel, you can find all recording of the previous events on the channel. Also, today event will be uploaded to the channel. And now we make some physical meetup. The first informal meetup was in Accra, and we hope soon to make another meetup in Cairo for members are in Cairo, are in Egypt. So we are now growing. Yes, you can continue, Juliet. Hello. Juliet, can you hear me?
I think she has a problem with her connection.
I can hear you.
Okay, great, great, Juliet.
Sorry, my network is just not stable and it's very frustrating. So sorry about that.
It's okay, Dr. Noha, can you keep going?
Okay, some highlights about our mentorship program. As Juliet said before, this program is only for women and the members of the community. We have till now we have 3 cohorts. This is the numbers of mentees and mentors of every one of them. Now it's a summary about our community. As I tell you now, we have created a platform which is a source of motivation for African women to take up career paths in GIS. We aim to expand in the coming years to support more African women in the GIS industry, introduce the younger generation to GIS careers, help Africa benefit from the applications of GIS application, and its related fields, as well as fundamentally bridging the gender gap in the Africa geospatial industry. We are open to fellow African women in Africa or the diaspora who wish to join our Slack and WhatsApp groups. You can follow us and register to the community. I sent the link to the chat box. I will send it again now. And thank you so much. Okay, thank you all. Thank you, Dr. Ali, and your team. Thank you. Thanks to all who participate to our event today. Thank you, Safinaz and Juliet.
Thanks, Dr. Noha.
Thank you. Thank you, Dr. Ali. Thank you, Dr. Noha. Thank you, everybody, for attending.
Thank you all. I'd like at the end to thank special thanks to Dr. Noha, who has been following up with us throughout the past couple of days to prepare for this webinar. Thank you, Dr. Noha.
You're welcome, Dr. Ali, and thank you. We are honored to be with us today, and we are looking forward to cooperate with you again in the upcoming events.
Okay, thanks, Dr. Ali, and I wish you speed recovery because your voice, wish you will get well soon.
Thank you.
Okay, now we can end our session today and hope to see you in the next and upcoming.
We will have one on 10th of June. We will send the registration link once we create it. Thank you all, and special thanks for our moderators, Dr. Noha and Juliet. Okay, have a good day and have a good night.